Hello guys, so we are going to continue the discussion with respect to linear algebra. In this particular video, we are going to discuss about a very important topic which is called as eigenvectors and eigenvalues. Now, in order to make you understand much more in a better way with respect to eigenvectors and eigenvalues, what I'm actually going to do is that I am going to probably show you this visualization page, okay? And this entire link will be given in the resource section of this video. So please go ahead and have a look onto that. But the basic agenda is basically to explain you what exactly is eigenvalues and eigenvectors with respect to this particular diagram, okay, or this visualization diagram. So first of all, over here you will be able to see that I have a lot of options like show in and out vector, show determinant, show eigenvectors, right? So let's consider over here, okay? So let's say that I have a matrix, right? One coordinate is over here. This is denoted by 1, 2. Okay, please have a look onto this particular point, right? So I have one coordinate over here, 1, 2, and the other coordinate over here, 3, 0. And you know that this is my vectors, right? This is my unit vector, right? Unit vector with respect to I and unit vector with respect to J. Okay. This matrix, let's consider that this is my linear transformation matrix. That basically means once I perform a linear transformation on this particular vector I and J, I should be able to reach to this specific points, right? So here what is basically happening is that when I have this unit vector I and J, once I perform the transformation, here you can see that my new specific points are 4 and 2, right? So here you can actually see it's nothing but 4 and 2. So once I'm actually performing this transformation from this point, it is basically going to this point. Okay. So, and I hope everybody understands about transformation. Now this is perfectly fine. Okay. Now let me do one thing. Here there's an option of show determinant, right? And I've already told you what exactly is the determinant. After the transformation, you will be able to see that this line is also getting squeezed. This line is also getting squeezed. Now what is the area of this particular entire area, or you can also call this as trapezium, right? Initially it was square, but after transformation you are getting a trapezium. So this is nothing but it is called as determinant, and I've already shown you with respect to the formula how to calculate the determinant. Okay, now let me uncheck this. Okay, and let me do one thing. Let me just go ahead and click on show eigenvectors. Okay, so here there is also one more option which is called as show eigenvectors. Now once I probably do this transformation, here you can see I'm getting two lines. One line is this and one line is this, right? One line is this and one line is this. I will talk about this importance of this particular line, what exactly this line is, because when I clicked on show eigenvectors for this matrix, that is 3, 0, 1, 2, right? We are actually getting these two vectors, right? Which is also called as eigenvectors, but I'll talk about the importance of these eigenvectors. So let me go back again. Now let me just go ahead and click on one more option that is called as show in and out vector. Okay. Now when I click on show in and out vector, let's consider another vector over here. And this particular vector here, you can see some values are over here, right? With respect to this particular vector. Now this vector position is nothing but 1, 1, right? 1, 1. So when I am doing, if I'm having this specific vector 1, 1, right? Here when we are doing this dot product with this particular matrix, I am actually getting this specific transformation, right? That transformation is nothing but 4, 2, right? So you can just imagine this is my final transformation result. And over here for this particular vectors, you can also see. And one more thing that I really want to show you over here, I'll just go ahead and uncheck show eigenvectors. When I probably transform this, here you can see that, or if I just go ahead and consider this as my line, let's say that I've gone and extended this specific line over here. Let me just reload this so that you'll be able to get a clear idea, okay, what I'm actually saying. So let's say that this is my entire line, and again this line can be extended till here. It can also be extended in the negative direction, right? Because it can just be multiplied by a scalar value and it can be extended. Now once I probably do the transformation, here you can see the squeezed new line is actually coming in a new direction, right? It is somewhere coming over here, right? It is coming over here. Here you can actually clearly see this, right? So for this particular vector, when I perform this kind of transformation with this matrix, you can actually see my new value is nothing but 4, 2, right? So here, if we go ahead and see with respect to this particular vector, it is nothing but 4. 1 unit, 1, 1 unit, 2 unit, 3 unit, right? And with respect to this 4 unit. So 4 is over here and 2 is on the y-axis, 1, 2. So this is my new position of this particular vector, right? So when I take this particular vector, when I apply this transformation, I'm getting this particular value, right? So here you can actually clearly see this, okay? Now for this particular vector, you can see that once I'm performing the transformation, I'm getting some different value, okay? Now let's consider some more vectors over here. Let's say that I have one more vector over here. Let's consider this is my vector, okay? I'm just going to consider this is my vector, okay? And this vector, we are just going to consider this as, or I will just go ahead and write it over here. Okay, I'll make this point over here. It is approximately minus 2, 0, okay? Over here it is minus 1.97 and 0.01, but we'll consider this as 2 minus 2 comma 0. Now see, once I apply this vector transformation with respect to this particular matrix, what will happen now? See the magic. What is basically happening? Now this has got completely squeezed to how many units? Minus 6, right? 1, 2, 3, 4, 5, 6. Now you have got this minus 6, and this is almost 0 on the x-axis, on the y-axis that is almost 0. The origin is same, but when I did the performance of this particular transformation, it is still in the same direction. Before we got in the other direction, the vector from here, it went to other direction, but right now this vector is still in the same direction. Now let me just go ahead and uncheck this show eigenvectors, okay? Now let me do the transformation. Here you can see the eigenvector is also passing through this, right? Now I hope you are able to understand the difference between an eigenvector and a normal vector. Why this vector is basically called as an eigenvector? Because once I perform the transformation, this is not changing the direction. This is probably getting scaled up, right? It is getting scaled up over here, right? Over here, you can see clearly it is getting scaled and it is in the same direction. So we can basically call this particular vector as an eigenvector. Similarly, do you think we can get another vector similarly? Right? Let me just go ahead and see this. Let me just go ahead and put this specific point over here. Now, if I'm performing this transformation with this matrix, then what is basically happening? This is going in another direction. So this cannot be an eigenvector. Okay. But what about this particular point? Let's see this. Let's say that here I have one point over here. Let's go ahead and consider this particular point. Now for this point, for this particular vector, the value is minus 2, comma 2. Okay, let's consider this. If I am actually performing transformation, this is also coming in the same direction. So this point or any point in this specific line, if I am performing a transformation with this matrix, this is also gonna be a eigenvector because it is still in the same direction. Now I hope you are able to understand the difference between an eigenvector and a normal vector. If this is my point, if I am performing transformation, here you can see this line is completely in, like when it is getting scaled up, it is still not passing to the same line. It is going somewhere else. It is also called as span, right? But if I talk with respect to this particular matrix, there are two vectors that we can actually see. Now in these two vectors, if the vector are in any point, if we just do the transformation, it is just going to scale in that particular vector. Let's say if I take this as an example, here my value is minus 2, 0. If I try to do the transformation, it's just going to scale by some units from the origin, right? And by which, how much units, right? Initially, if I go ahead and see, this is my vector at minus 2, comma 0. Let's say if I'm scaling this, or if I'm performing a transformation with this matrix, how many units it is scaling? 1, 2, 3, 4, 5, 6. Since it is scaling by 6 units, so the eigenvalue for this vector, so let me just go ahead and write it down. The eigenvalue for this eigenvector, the eigenvalue for this eigenvector is nothing but it is 6. It is 6. Sorry, it's not 4, 6. Right? Why it is 6? Because initially my point was somewhere here, but now it got squeezed till this point, right? After performing the transformation, and it is in the same direction of this particular vector, right? Initially my point was here, but still it is in the same direction, right? It did not change the direction, and this entire direction is basically called as a span, right? I may also have one vector over here. if I probably try to do the transformation, it will probably extend it. And if it stays in the same direction, this is also an eigenvector. This is also an eigenvector, right? So let me just go ahead and again reload and show it to you multiple examples. So with respect to any metrics that you have over here, any transformation metrics you have, if I just go ahead and consider any eigenvector, right? So let me just go ahead and consider one vector which looks something like this, right? If I perform the transformation, you will be able to see that it will still get extended in the same line. So I can also consider this vector as an eigenvector. So similarly, for every different transformation, you will be able to find out the eigenvectors. By how much unit it is basically getting squeezed, that is actually called as eigenvalues, right? So I hope you have understood the basic difference between eigenvalues and eigenvectors, right? So let me go ahead and probably do this a problem statement for finding how do you find out this eigenvectors and eigenvalues. Okay, so first of all, we'll go ahead and do the definition. So here eigenvectors and eigenvalues are fundamental concepts in linear algebra that have numerous application, and it has numerous applications because we will be seeing one algorithm which is called as principal component analysis, and there these eigenvectors and eigenvalues will specifically be used. Okay, they provide insights into the properties of linear transformation represented by matrices. Okay, now let me do one thing over here. So first of all, I have already told about what exactly is the definition of eigenvalues, right? So if I go ahead and talk about eigenvalue, this is specified by lambda. Okay, so eigenvalue is nothing but it is a scalar. It is a scalar that indicates how much an eigenvector so for every transformation, there will be some eigenvectors, like that two lines we have actually seen, right? And eigenvector over there is nothing but it can be stretched with some kind of scalar value, right? So here, how much an eigenvector is basically stretched or compressed during linear transformation. Okay, so this is what eigenvalue is. Okay, and similarly, if I go ahead and discuss about what exactly is eigenvector, it is, and this is also denoted by V, it is nothing but a non-zero that only, a non-zero vector, I can say. It is a non-zero vector that only changes in scale. Okay, that only changes in scale, not direction. This is important, not direction, right? When a linear transformation is applied, and this is also a very important property. Whenever we perform a linear transformation, the origin will be same, the lines will only be changing, and it should be only a straight line, right? So this is what an eigenvalue and eigenvectors are. So usually, again, I'm not going to prove this specific formula. If you really want to calculate the eigenvector, it is given by this particular formula. Okay, so here A, the transformation. So here I can go ahead and write for square matrix A, and eigenvector and its corresponding eigenvalue satisfy the above equation. So this is the equation that we specifically use, right? And let's take one specific example. Let's say if my matrix is A 4 1 2 3. Okay, so we will also go ahead and take this particular matrix over here, right? So how do I go ahead and write 4 1 2 3? So it is nothing but 4 2 1 3, right? So 4 2, so I will just go ahead and write this 4 4 2. So this will be my 4 units and this will be my 2. Okay, so this is the point 4 2. Okay, it is approximately near, but just exactly to make it point over here is difficult. Okay, so this is 4 2. Let's consider this as 4 2. And 1 3. 1 3 is nothing but where do I specifically get 1 3? So 1 3 is nothing but this and this, right? So here, if I just go ahead and click on my show eigenvectors, so this should basically be my eigenvectors, right? At this particular point, the C value can be anything, right? The eigenvalues can be anything, but we should probably get any of these particular vectors over here, right? So these are the two vectors that we should be able to get, right? And out of it, we'll just try to go ahead and calculate about one vector, and let's see how to do that, right? So here, let's go ahead and solve this. So here I have this A, okay? First of all, what we'll do is that we'll go ahead and calculate our eigenvalues. So in order to find eigenvalues, okay, so here we will go ahead and write determinant of A minus lambda I, okay, is equal to 0. So this is how an eigenvalues will be calculated, and this is specifically using this particular equation. Again, I'll not go ahead and derive it, but we can just go ahead and consider this as an equation, okay. The reason why I'm not deriving it, because guys, as a data science person, right, you'll be able to see that most of the work will be specifically done by coding, right? It's more to understand about the fundamental concepts and all, right? So now let us go ahead and solve this A minus lambda of I. What is A over here? It is nothing but 4 1 2 3, okay. And then I have specifically, when I say lambda of I is nothing but identity matrix. So if this is 2 cross 2, it will be 0 lambda 0 0 lambda, and finally I will be able to get 4 minus lambda, because we are doing the subtraction. Then I have 1 minus 0 2, and we have 3 minus lambda, right? So once we specifically do this particular calculation here, now how do we calculate it in order to find out the determinant, right? Because here we need to calculate the determinant of A minus lambda I. Determinant is basically just multiply both them, right? So here I have 4 minus lambda multiplied by 3 minus lambda, and it will be nothing but minus 2 multiplied by 1, right? And then I have 4 minus lambda, 3 minus lambda minus 2, which is nothing but, if I do this multiplication, what it exactly is, 12 minus 4 lambda minus 3 lambda plus lambda square, and then I have this minus 2. It is nothing but lambda square minus 7 lambda plus 10. Okay, so this is what I'm actually getting at. Okay, so guys, the next step over here will be to probably solve this equation. Now in order to solve this equation, again, we need to probably go ahead and solve this with the help of quadratic equation, okay? And I don't know how many of you remember this or not, but we can go ahead and write lambda square minus 7 lambda plus 10 is equal to 0. And when we are solving this specific equation for quadratic equation, this lambda value can be specified as minus b plus or minus b square minus 4ac divided by 2a. Don't worry about this specific equation if you don't remember it, but this is how we can solve quadratic equation for lambda. Okay. Again, the reason why I'm not deriving this, because it is not that important for data science, because automatically all these things, there will be a functions written in Python where we can specifically implement it. Now when we are using this particular formula here, you can see that A will be 1, right? And your B will be minus 7. So this is B, this is A square minus 2ab plus B square, right? So something like that. And here, A will be over here, B will be over here, and this C will be my constant, right? So 10 over here. So if I go ahead and write lambda is equal to 7 plus or minus root of 49 minus 40 divided by 2, which is nothing but 7 plus or minus root 9 divided by 2. So finally I'll be getting my lambda. If you go ahead and do the calculation, I'll be getting 2 lambda values. Okay, so here, since this is plus or minus, okay, so my lambda 1 will be nothing but, we can take 7 plus 3 divided by 2, and lambda 2 will be nothing but 7 minus 3 divided by 2. So here I will be getting my lambda 1 as 5 and lambda 2 as 2. I hope you may have seen this somewhere, right? In obviously the school days, how to probably go ahead and calculate this, right? So these are my eigenvalues of the matrices A. Okay. Now finally, the second step will basically be to find the eigenvectors. Now, in order to find out the eigenvectors, we can go ahead and write this formula: A minus lambda I u multiplied by vector v is equal to 0. So for lambda 1 is equal to 5, I'll just go ahead and replace this. So I will just go ahead and calculate A minus 5i, which is nothing but, here we will go ahead and write this. So let me go ahead and write it over here. So A, everybody knows what exactly A is. So A is nothing but 4, 2, 1, 3, and 5 of I. When I do 5 of I, it is nothing but 5, 0, 0, 5, right? So we can further do this calculation. So here, if I subtract this, 4 minus 5 is 1, minus 1. This will be 1, this will be 2, this will be minus 2, right? So here is my all the values, right? Here you know that we also need to multiply with the vector, right? So vector can be anything. Let's say if we are taking x and y as my vector, okay, this will specifically be multiplying, right? So let me do one thing. Let me go ahead and write like this. So this will be my value: minus 1, 2, 1, minus 2. This, when we multiply with x and y, or when we do the dot product, I should be getting 0, right? We here, like how we have written, right? So if we solve this equation, it is again very simple. This will basically reduce to minus x plus y is equal to 0. So here I can go ahead and write y is equal to x. Okay. Now y is equal to x in this particular case, this reduces to y comma y is equal to x for one of the lambda value. Similarly, for lambda is equal to lambda 2 is equal to 2. We can again do the calculation. Again, I'm just doing it so that at least for those people who knows this, they should be able to understand it, right? So 4 minus 2, 1, 2, 3 minus 2. And finally, I'll be getting 2, 1, 2, 1, right? So if I take this 2, 1, 2, 1 and multiply with my vector xy, it is nothing but we are basically going to work with 0. And here, this will specifically be reducing to 2x plus y is equal to 0. I can also go ahead and write is equal to y is equal to 2x. So this is my second important corresponding vector. So here you can actually go ahead and write an eigenvector corresponding to lambda 2 is equal to 2, right? So this is what I'm actually going to get. So here, in order to probably talk about this, let's say that my A matrix is 4, 1, 2, 3, okay, and it has this eigenvalues. Lambda 1 is equal to 5, lambda 2 is equal to 2. Then for lambda 1, okay, is equal to 5. My vector v1 can also be written by over here. If I specifically want to return it or write it, here you can actually see that based on this, let's consider this. First of all, it is y is equal to x. When I say y is equal to x, so whenever x is 1, y will also be 1, right? If x is 2, y will also be 2. Similarly, for lambda is equal to 2 is equal to 2, my v2 will be nothing but y is equal to 2x. Y is equal to 2x basically means if I am specifically going to calculate, sorry, it should be y is equal to minus 2x. Okay, y is equal to minus 2x. So here you can see y value is nothing but minus 2x. So if my x value is 1, this will be minus 2. So here you will be able to find out both this, right? When I say y is equal to x, because y is also, if x is 1, y will also be 1. So here, since both are equal, I'm just going to take this as 1, right? So this is about eigenvalues and eigenvectors. I know I have not focused much on the calculation part, but I feel that, it is not that important. But the concept is important because this concept will be applied in one of the algorithm which is called as dimensionality reduction. So where this will specifically be getting applied, the application part, it will be specifically applied in one algorithm which is called as principal component analysis. So here we will be specifically doing dimensionality reduction. So that is where this will basically get applied. But remember, I think some or the other way in the college, in the school, you have solved this equation, right? So y is equal to x, 1 I got, y is equal to minus 2x. So that is why for lambda is equal to 1, my eigenvector is nothing but 1, 1 and 1 comma minus 2. So for any 2 cross 2 matrix, you will be getting 2 vectors and that will be there. And final conclusion or interpretation, I can basically write these eigenvectors and eigenvalues describe how the matrix A scales and rotate vectors into its transformation. Eigenvalue indicate the factor by which eigenvector is stretched or compressed, and eigenvector provides the direction in which this stretching or compression occurs. The reason we have initially seen the equation A vector is equal to lambda vector. This is what it is basically saying, by how much eigenvalue this is stretched, right? This vector is stretched. This is what this entire equation is. But in order to calculate it, we need to find out determinant and many more things. So I hope you like this particular video. This was it. As I said, the application will be specifically in dimensionality reduction. Okay. And you will be seeing this algorithm in this particular course. I will be uploading after we probably discuss differential equations, right? So yes, this was it from my side. I will see you all in the next video. Thank you. Take care. Bye-bye.